Hello and welcome to my channel Learning with Sarita. In this session we will discuss the topic electrostatic potential energy of a dipole in uniform electric field. All the terms are familiar terms and we will take a quick recall of all the concepts. For electrostatic potential energy, we carry a charge from infinity and bring it into the region of the electric field. So work done to carry the charge from infinity is taken as the potential energy. That is, the difference in potential energy is given by K Q1 Q2 by R. And dipoles are equal and opposite charges separated by a small distance. They are pair of charges of equal magnitude and opposite sign and separated by small distance. And next is the uniform electric field. They are of same magnitude and are in same direction. That is, the electric field strength at all points will be same. For our topic, we consider a uniform electric field and we place a dipole in uniform electric field. What happens when a dipole is placed in uniform electric field? The plus Q charge experiences a force plus QE in the direction along the direction of the electric field, and the minus Q charge experiences a force minus QE in the direction opposite to the direction of the electric field. So the net forces, that is the total forces plus QE minus QE, will be equal to 0 when we place a dipole in uniform electric field. But these two forces plus QE minus QE are the couple forces. What they do is they produce a rotating force torque. Due to this couple force, the dipole experiences a rotating force torque and it tends to rotate along the direction of the electric field, tends to rotate towards the direction of the electric field. And due to this rotating force, the dipole makes an angle theta dash with the electric field. That is, what's the concept when we place a dipole in the uniform electric field? On placing the electric dipole in uniform electric field, the net force is 0. That is, plus QE minus QE is 0. Only torque will be acting on the dipole. The rotating force will be acting, and this force and this rotating force tries to align the dipole with the electric field. Task of our topic is to find electrostatic potential energy that the dipole can possess. Once we place a dipole in uniform electric field, it is making an angle theta dash with the external field. Now, to calculate the potential energy, we have to do some work, because potential energy is nothing but the work done. So in what way we can do a work on a dipole? The only possibility to do work on a dipole is to make the dipole to rotate in opposite direction. That is, once the dipole is placed in uniform field, it rotates in the clockwise direction towards the direction of the field. How we can do our work? We can make the dipole to rotate in anti-clockwise direction opposite to the direction of the field. Okay. That is, the torque naturally existing makes the dipole to rotate in this direction, and the external torque which we are giving is in the opposite direction. Now we will just compare the work done when carrying a single charge and on a dipole. For a single charge, the work done is to carry the charge from infinity. And for a dipole, the work done is to rotate the dipole. And in the case of a charge, the Coulomb force and the external force are equal and opposite. And the torque due to the couple force and the torque externally applied are equal and opposite. And for a single charge, the charge is carried with constant velocity, and for a dipole, it should be rotated with constant angular velocity. Here work is done to rotate the dipole in the anti-clockwise direction. I rotate the dipole to an angle d theta. Initially, the dipole is making an angle theta dash with the field. Against the field, I am rotating to an angle d theta. So, theta dash plus d theta will be giving theta. That is after work done, that is after the dipole is rotated, the initial angle plus d theta will be giving the final angle theta. Here I have a formula collection for torque. We know that torque is the rotational force, and torque is given by the product of the perpendicular distance and the force. Tau vector is equal to r vector cross f vector. And when we discuss in the case of electric field, we give tau vector is equal to p vector cross e vector. And some more formulas for torque is the rate of change of angular momentum, and the torque is the product of moment of inertia and the angular acceleration. The formula which we are going to use now is tau vector is equal to p vector cross e vector. Now let me see how we get the expression from r vector cross f vector. Torque is the product of perpendicular distance and f. Now we have to find the perpendicular distance between the charges of the dipole. Here we have placed the dipole, plus q and minus q charges are here. What is the perpendicular distance between the two charges? So I drop a perpendicular here and mark this point as O. Here is our angle theta. Now we have to find this side OB. Here the triangle BOA is a right angle triangle. So I can easily apply the Pythagoras theorem to find the angle theta. Here sin theta is equal to OB by 2A. My hypotenuse side is 2A, that is the length of the dipole. So sin theta is equal to OB by 2A. R perpendicular is equal to 2A sin theta, and the force in the field we know is plus QE, and tau is equal to 2A sin theta into QE, and tau we get it as PE sin theta, because the product of the charge and the length of the dipole is the dipole moment P. This is the value for magnitude. On introducing vector notation, I get tau vector is equal to p vector cross e vector. The work done to rotate the dipole by external torque is given by integral theta dash, that is theta initial to theta final, tau external vector d theta. Here the torque which is applied externally is equal and opposite to the torque which is created by the electric field. That is, they both are equal and opposite in directions. Here we are going to take only the magnitude values, because the dipole moment P and the electric field will be of same value. The only variable which will vary is the theta. For different theta values only we are going to calculate the values of work done. So I take the magnitude formula. So tau external vector mod is equal to minus tau field vector mod, that is equal to p vector cross e vector mod, that is PE sin theta. Now I give PE sin theta to the expression tau external vector. So integral theta dash to theta PE sin theta. Here I take PE outside, and then integral sin theta is minus cos theta, and I get the expression PE minus cos theta final minus of minus cos theta dash, that is initial. So the work done, which is change in potential energy, will be U of theta final minus U of theta initial, that is minus PE cos theta final plus PE cos theta dash initial, and the del U will be minus PE cos theta final plus PE cos theta dash initial. Here in this point, I would like to recollect a basic concept. Whenever we calculate the potential energy, we consider the reference point, that is the initial point, to be 0. For this, you recollect the example. When we place a book on a floor, the height h will be 0. So the potential energy when a book is placed on a floor will be 0. When I raise the book to a particular height h, it gains some potential energy. So what will be the work done? The change in potential energy. Initially, the value will be 0 because initially it is on the floor. This is in the case of a book. Now we come to the case of a charge. When I carry a charge from infinity, I bring the charge from infinity into the region of the field. Initially when the charge is in infinity, what is the potential? The potential is 0. That is, at the reference point, the potential is 0. From the region of potential 0, it is gaining potential when entering into the field. Okay. In the case of book, initially it is in the floor and then it is gaining energy when work is done. And for a case of a single charge, initially the charge potential is 0 and when some work is done, it is gaining the potential. And here in the case of a dipole, I am going to take the reference to be 0. I can take the reference to be 0 only if this value initial angle is 90 degree. So I take an assumption that initial angle theta dash initial to be 90 degree. What happens to my equation? Minus PE cos theta final plus PE cos 90. Cos 90 is 0. Cos 90 becomes 0. So the expression holds only the theta with final angle. Okay. So U is equal to minus PE cos theta. And this is the magnitude value. Here I want in vector notation. So I give U is equal to minus P vector dot E vector. So finally the concept here is the electrostatic potential energy of a dipole is depending on the dipole moment, depending on the electric field, and also on the angle theta between the dipole moment P and the electric field. Now we are going to discuss some cases for varying angles of theta. First, I discuss the case when angle theta is 0. Here you see I have placed a dipole in uniform electric field. That is, the positive charge of the dipole is on the negative side of the field and the negative charge of the dipole is in the positive side of the field. What will be the condition of the dipole in this state? It is parallel to the electric field. That is, the dipole moment and the electric field are parallel. One more concept easily we can say is the positive charge is attracted towards the negative side and the negative charge is attracted towards the positive side, and so the dipole is very comfort to be staying in this condition. That is, it easily sits into to stay in this region because its opposite charges are attracted and it can be easily staying in this condition. That is, there is no need of any external work to make the dipole to stay in this region. Now we can see what is the value of E in this condition. P vector and E are parallel. That is, the angle theta is equal to 0 and U is equal to minus PE cos 0 degree. We know cos 0 is 1. So U is equal to minus PE. That is minimum value of potential energy. Angle theta is 180 degree. For angle theta is 180 degree means this positive charge must come to this side and this negative charge must come this side. That is, I have to rotate the dipole to an angle of 180 degree. I have to rotate the dipole from this angle to this angle. So once I rotate, I have to do some more work to rotate the dipole. See, once I come here, the dipole is experiencing a repulsion because here positive charge is entering into the positive field and negative charge is entering into the negative field. So I have to do more and more work to make the dipole to bring to this condition, that is to rotate to an angle of 180 degree, and the dipole is not more comfortable to stay in this condition because due to repulsion, this side positive positive, this side negative negative. So I have to do some work to make the dipole to hold in this condition, or else it will undergo repulsion and move away from this state, isn't it? So I am doing more work to make the dipole to stay in the condition of 180 degree. So when the angle theta is 180 degree, the dipole moment P and the electric field are anti-parallel to each other. So I give theta angle 180 degree. So I get minus PE of minus 1. So PE value is maximum when the dipole moment and the electric field are anti-parallel to each other. Okay guys, after watching the video, you smash the like button, share my video and subscribe to my channel and travel with me to get full mark easily. Thank you.